Hi, this is Dr. R. Vijay Chandra. In this video, let's see about inner product spaces. So, what is an inner product space? A space V is said to be an inner product space if the following conditions hold. Let V, U, V, W are the vectors in a vector space, capital V, and C be any scalar. An inner product on V is a function that associates a real number u comma V. Well, of course, it is a notation for inner product space u comma V. With each pair of vectors u and v and satisfies the following conditions. Inner product u comma V must be equal to inner product v comma u. Second condition is distribution property, which is called as distribution property. Inner product u comma v plus w equal to inner product u comma v plus inner product u comma w. Third one is associative. K is a scalar here. K into inner product u comma v equal to inner product au comma v. Fourth condition is inner product of v comma v is always greater than or equal to 0. That is non-negative. If inner product v comma v equal to 0, if and only if v equal to 0. That means v is 0, inner product is also 0. Inner product of v comma v is 0, that means the vector v is 0. So if these conditions are satisfied means we call that set capital V, that is a vector space, becomes a inner product space. Here we denote u dot v. It represents dot product. Inner product u comma v, that is general inner product. It is a notation. Here we denote a vector space as within bracket v comma plus comma dot. This is a notation. Here we denote inner product space as v comma plus comma dot comma the notation for inner product. Right. Here we see the properties of inner product space. U, V, W are the vectors in an inner product space and C is a real number means these are the properties. The first property is inner product 0 comma V is equal to inner product V comma Z, that is obviously 0. U plus next property states that inner product U plus V comma W equal to inner product UW plus inner product V comma W, that is distributive. Then C is a scalar, inner product U comma CV is equal to C into inner product U comma V. So very important properties which we will be using in the concepts of in many concepts of inner products. Here we see the definitions for norm, distance, angle and orthogonal. Norm is nothing but a length. We call length of u. Norm of u or a length of u. So norm of u is nothing but square root of inner product u comma v. And the distance between two vectors is defined as norm of u minus v, which is square root of inner product u minus v comma u minus v. Then the angle is defined as cos theta equal to inner product u comma v divided by norm of u into norm of v, where theta lies between 0 and pi. Then we come across orthogonal. So two vectors are said to be orthogonal means the condition is inner product of those two vectors equal to 0. That is the notation is u perpendicular, that is u is orthogonal to v. So if this happens means definitely the inner product of those two vectors equal to 0. Then these are the properties of norm. So norm of u is always greater than or equal to 0. Then if norm of u equal to 0, then always u equal to 0. The third condition is norm of cu equal to mod c into norm of u. Then this is the property of distance. So we see the property of distance. D of u comma v is of course greater than or equal to 0. D of u comma v equal to 0 means definitely those two vectors coincide. Then distance between u comma v is same as distance between v comma u. Next, we see the Cauchy's squares inequality and triangle inequality. That is, U, V are the vectors in an inner product space V here. Cauchy squares inequality is defined as norm modulus of inner product U comma V less than or equal to norm U into norm V. We see the proof later. Triangle inequality. It states that norm of U plus V is less than or equal to norm U plus norm V. Then the Pythagorean theorem. V, U are orthogonal if and only if norm of U plus V the whole square equal to norm U square plus norm V square. So which is called Pythagorean theorem. So these three results are very important in inner product spaces. Then next we see orthogonal vectors. Two vectors u and v are orthogonal if u dot v are equal to 0. That is already we see. The vector 0 is said to be orthogonal to every vector because 0 into any vector equal to 0. Therefore we say that 0 vector 0 is the 0 is orthogonal to every vector. Finding orthogonal vectors. Here it is an example for finding orthogonal vectors. Determine all vectors in R power n that are orthogonal to U equal to 4, 2. Here U is given, that is the vector is 4, 2. That is, we are finding orthogonal vector V. U is given as 4, 2. Let V is equal to V1, V2. We assume that V is equal to V1, V2. Right? Then it is given use, we are finding the orthogonal the vector which is orthogonal to U, so that we assume that U dot V is equal to 0. So U is given 4, 2 and we assumed V is equal to V1, V2. Just multiply 4v1 plus 2v2 by the addition law. We by the multiplication of inner product, just we get the result 4v1 plus 2 into second coordinate v2. So therefore u dot v equal to 0. So 4v1 plus 2v2 equal to 0. So here we make this assumption. We assume that v2 equal to t. So substitute here 4v1 plus 2t equal to 0. From this, v1 is obtained as minus t by 2. So v1 is equal to minus t by 2, v2 equal to t. Therefore, v is equal to v1 comma, we assumed that v is equal to v1 comma v2. So substitute the values here. v1 is minus 2 t by 2 comma v2 is equal to t. So we have obtained the vector which is orthogonal to u. Here, next we see the definition of orthogonal basis. Orthogonal basis, that is, for any vector a comma b in B, A is orthogonal to B. If A is orthogonal to B means inner product a comma b equal to 0. Orthogonal vectors means inner product a comma b equal to 0. 0 vector is orthogonal to every vector. That is also we know. An orthogonal set is a set of all pairs of distinct vectors. So orthogonal set S is a set such that all pairs of distinct vectors are orthogonal. So if you want to say a set capital S is orthogonal means for every pair, if you consider any pair of vectors in that set, that is also orthogonal to each other. That is the main. An orthonormal set. So come to orthonormal set. An orthonormal set is an orthogonal set of unit vectors. So orthonormal set is defined as orthogonal set of unit vectors. Every non-zero finite dimension inner product space has an orthogonal basis. Next we see orthogonal complement, the definition of orthogonal complement. Here W is a subspace of an inner product space V. A vector U in V is orthogonal to W means if it is orthogonal to every vector in W. W is a subspace here, V is an inner product space. If you consider a vector U in V If it is orthogonal to W means if it is orthogonal to every vector in W, then only we say that W, the set of all vector in V that are orthogonal to W is called orthogonal complement of W. So orthogonal complement of W means each and every vector in V is orthogonal to the vector in W. So then only we say that W has a orthogonal complement. So orthogonal complement is denoted by the symbol W orthogonal complement. Thank you. Thanks for watching.